Hi, everyone. So I'd like to continue on this topic by presenting few things about this AMV experiment that Johan presented and that we're doing in coordination with the NCAR folks. And so this is all the credits for this work really go to Johan. He's doing all the work. He's the brain here. And this is a work supported by NOAA Climate Program Office, and I really acknowledge their support for doing this work. So a few things I'd like to touch about this experiment. It's more like you saw the nice science result from Johan, and I would like to touch a few points. What did we learn from this AMV experiment that are really relevant for this component C that we're trying to design? And I want to remind you that our goal here was to test with this AMV fixed pattern, this experiment where we have a fixed pattern AMV as a first test before doing pacemaker experiment with this pattern. And so we have gone through a number of issues and struggling with a number of issues that I think can be relevant to the design of our experiments here. And so I'll start with one, and I hope I'll have time to touch all of these. And one is the model drift that we find when we run this experiment. So I won't spend much time on the protocol because Gökhan and Johan already talked about it. So we're just restoring our model to this AMV pattern. And here I'm going to focus mainly on the difference between AMV plus and control experiment. And so reminding you that the reason we are restoring here to this pattern, so we restore because we expect by putting heat there in the North Atlantic, we might change the subsurface circulation in the Atlantic. And we don't want these anomaly to communicate to the surface and then affect the atmospheric response or communicate through the subsurface to other ocean basins. So we want to make sure by imposing this restoring that we keep the pattern we want to test the impact on. And so the goal is to find a right restoring timescale that doesn't perturb too much the timescale, as Christoph pointed, but that still keeps us our pattern. And so we use here quite many members in our experiment to test the result. And Johan said that we focus on 10-year long experiment, but actually every single experiment was run for 20 years for testing. And here it's going to be very useful to use these 20-year experiments. Okay. So this is the sea surface temperature wintertime evolution in this AMV plus minus control. I just selected few years to show you that after 3-4 years, there is a cooling that appears in the North Atlantic despite this 5-day restoring that we're imposing. And you see that it's not significant in year 4, but it really develops, and after year 10, 20, it's really strong cooling there. And this is the surface, and so we have attributed this cold drift to a weakening of the Atlantic meridional returning circulation. So does it matter for our experiment? So it matters if this cooling at the surface is going to affect the climate response. And I want to know here, after how many years does it matter? And so I'm showing here the average for this response for year 2 to 11, wintertime, summertime at the bottom, and I'm showing air temperature and sea level pressure. So if you look at the first 10 years of the simulation, the air temperature doesn't show much of a cooling here. Still the warming dominates. And we have in winter this negative sea level pressure. And interestingly, the summertime doesn't show much of a cooling because really this is a winter phenomena related to this deepening of the mixed layer that affects this evolution of SST. So we could say that the first 10 years, there is not much impact of this cooling, even though it's not clear if this part of this sea level pressure response is not affected by some of this drift. However, if we look further in time, the next 10 years of the experiment, year 11 to 20, this is sea surface temperature in addition, and this cooling now can be seen in the air temperature, and the sea level pressure difference reflect that cooling. So, and summertime is less affected, but there's some bulb of cooling that appear there. Okay. So why does it matter for this experiment? Here again, we're doing fixed pattern, but for this pacemaker AMV experiment, we want to prescribe the observed evolution of the Atlantic meridian, the Atlantic multi-decadal variability. And so in the transient simulation, there will be several decades where the AMV will keep the same sign. And so it means that we will have this drift that will appear, and we cannot really focus on just 10 years there. And so, and also because that drift will develop in the Atlantic and we are free coupled everywhere else, that drift at the subsurface will be communicated to other basins. So it's really problematic to interpret the impact of the AMV. So can we reduce this drift here in a protocol? So when we investigated the source of this drift, we were quite surprised to find that actually before even putting any AMV anomaly, we have a drift in our control simulation. Remember that before we impose this AMV anomaly, we have a control simulation in which we restore the sea surface temperature to the model's own climatology, right? And so here I'm showing result only from this control climatology compared to a free-running model where we don't restore anything. And what we find is at the subsurface, these are subsurface temperature anomaly average between 50 meter and 200 meter, we have a cooling that appears when we restore the model to its own climatology. I'm showing here 5-year averages. This is the second pentade minus the first, etc., going to year 16 to 20 of the simulation. So you see that the eastern subpolar gyre cools and seems like propagates over all the subpolar gyre, and the contours are climatology here. And again, this drift is attributed to a weakening of the AMOC. So in this control simulation, the AMOC weakens. So our hypothesis was what happens in this climatology run, why the AMOC weakens. Our hypothesis is that by restoring the sea surface temperature to its climatology, we are favoring weak AMOC state in this model. So to show that, I'm using the same plot as Johan showed earlier. I'm looking at the PDF of the AMOC anomaly in this control experiment where we restore the sea surface temperature to climatology compared to the free-running model with no restoring. So the three plots show the same type of thing. If we the black curve is the AMOC distribution for this control experiment. So this is a cumulative PDF. Here we reach 100%. And the black dashed line here, the vertical line, represents the mean state. So here we have in the free-running model, so this is the free-running model, sorry, in the black, we have like a Gaussian behavior. And the red lines represent this PDF in the experiment where we restore the sea surface temperature anomaly. So basically in the control run, you see that the values lie within the range between 3 Sverdrup and 2.5 Sverdrup, but when we restore to climatology, we really increase the spread of the AMOC. And here, sorry, I'm showing year 1, 10, and 20 year in the simulation where we restore the SST. So as we go along the simulation, we find that the spread in the AMOC increases, and also we favor weak AMOC states here. So why? One possibility here is that we're breaking the feedbacks in our system. So the AMOC is controlled by temperature and salinity feedbacks through the changes salinity and temperature affect mixed layer depth in the high latitudes. And so the hypothesis we're making is that we are favoring stronger positive feedback by restoring to temperature. So for example, if you start with a positive AMOC, that tends to give you more salty and warm water at the north latitude. So you bring more salty and warm water at high latitude. When you restore to temperature, you damp the warm anomaly, but you keep the salinity anomaly. So you favor a strong AMOC, and which strengthen your initial state. Same way, if you start with a negative AMOC, that brings you cold and fresh anomaly northward. Because of the restoring, you're going to damp the cold anomaly, but you keep the fresh anomaly that will tend to weaken even more this initial AMOC anomaly. So we favor in both cases strong positive feedbacks there. So then you will ask, why do you have always weak AMOC state in that case? And our hypothesis there is we favor weak AMOC state because a weak AMOC is associated with a shallow mixed layer depth. So it's easier to have an efficient forcing and efficient climatology restoring with a shallow layer than with a deeper layer. So how do we solve that? The response we found is we need to have a consistent relationship between temperature and salinity, and so we need also to restore to salinity. So we have made few tests here, again here just in this control, where we just restore in the control model by adding salinity restoring in addition to temperature. And here I'm showing the same quantity, this AMOC distribution, when now we restore both temperature and salinity with the same 5-day restoring timescale. And we find that this is the plot I showed earlier, just with SST. After 20 years, we had this huge increase in the spread. Now, when we restore salinity, you see that the spread is much, much reduced, okay? But it is still there is still a shift actually in the distribution. So can we do better? Which time scales should we use, is best to use? And so the good thing about this restoring experiment, you can save the heat flux you impose to see what are you trying to counteract in terms of anomalies. So here I'm showing this heat flux restoring term for different time scale restoring. And so the colors are these heat flux anomaly that we put to compensate for the drift basically in the model. So if it's red, it means that our model is drifting and cooling, and we need to compensate for that by adding some heat to the system. And we don't want to have any of that because this is going to affect the AMOC. So you see basically as you go to longer restoring time scale from 1 to 15, that we don't have any colors anymore here. So our system is adjusted. We're not perturbing it much, and we don't need to add any additional flux to keep the model close to its mean state. So the short answer here is that 15 days is our best restoring time scale, and it's consistent with what Christoph showed yesterday. Same thing shown now for the AMOC. Does that verify? I'm just comparing here this temperature and salinity restoring time scale. So what the AMOC distribution for these 3 different time scale restoring temperature and salinity. And you see that the red line is not as much shifted for the 15-day case. And so now we have our control experiment with this 15-day SST and SSS restoring. And we think now we have a stable initial reference run to start the experiment again. Right, so unfortunately we found that late. Okay, another subject now. I'm asking what's the respective role of tropical and extratropical AMV anomaly, in the sense that should we impose tropical or extratropical anomaly, or can we stop at 20 north? I think Johan gave you already convincing evidence that tropical anomalies were needed to get the Pacific response. And the reason I'm bringing this up is because in the discussion of this DCPP, we wondered whether we could stop at 20 north in the experiment we would propose. And here, so I'm just adding that I think we need to go south of 20 north in the experiment we will propose. And so here I'm showing the evolution of sea surface temperature anomaly in the no tropic experiment. So just if you impose the extratropical anomaly, and as expected, even if you don't put anything in the tropics, after a few years you do get tropical anomalies, right? So that was also, I guess, the motivation for only putting them in the extratropics. So we could have said it's okay, after a few years we still get the tropical response. But the thing is, even if we get them at the end of the simulation, they are weaker than if we impose them initially. So if they are important for this teleconnection, I think it's important to impose them. And it's more the case in winter than in summertime. So another way of showing it is just comparing the, what is that? This is the air temperature for this full AMV and no tropical AMV at the end, year 7 to 11, average over this year of the simulation. So if we have no tropics, after 10 years of simulation, we have weaker anomalies here, this is summer, than if we impose the full AMV, okay? And so we get a weaker Pacific response in this case than in this case. But actually, interestingly, we still have a strong response here. So in terms of sea level pressure also, we find that the full AMV case gives you a comparable response to the extratropical one, but the extratropical one is weaker. So again, if we want to have the full response, this is for summertime, average over 10 years, we need to have the full AMV there. Third thing, this to answer a question by Mingfeng, what happens in the winter? Why don't we get the NAO here? So Johan didn't have time to present it, but when we put this AMV anomaly, we expected to find negative NAO response in winter in the Atlantic based on previous work. And we find when we average the sea level pressure for this 10 years that we have this negative anomaly that I showed before. This is for winter time. And actually, so here, this is for 10 years, but as I showed that there's this drift that starts, to make sure I'm not contaminated by the drift here, I'm going to focus just on the first 4 years, just before that drift becomes significant. So if we look at this sea level pressure averages over the first 4 years of the simulation, and the difference again between AMV plus and the control, this is 500 hectopascal in shading, and controls our sea level pressure. We found that we have a positive NAO in winter here. So it's exactly the opposite to what we expect. But if we look at in the model, in the free-running model, the signature of the PDO, how the regression of this 500 hectopascal anomaly project in the Atlantic, it kind of resembles that pattern. So the hypothesis here, as Ming-Fong was saying, is that maybe we are contaminated by the Pacific teleconnection here for the winter response. And indeed, what Johan tested is he did another experiment, as he presented, by restoring the tropical Pacific to its climatology. And if we do that now, we have this nice negative NAO response that appear in winter. And if we now restore the global ocean, so having basically like an EMIP run, we find again this negative NAO response. So in other words, we think this AMV does lead to a negative NAO in winter, but it is masked by other teleconnection from the Pacific. And this is important to keep in mind if we propose a coupled framework for this experiment, that the interpretation of the results need to be cautious and keeping in mind that other teleconnection can mask local direct responses. Last thing I want to touch is we heard a lot about it during this workshop and our attempt to answer this question. How many ensembles do we need? So Gokhan showed that they use 30 members for now. We use 100. Do we need as many? We're also moving toward repeating the same experiment here with our high-resolution model, a 50-kilometer atmosphere. So this was all our test run, and we wonder how many members are we going to need even in this high-resolution model. So what's the magic number? The way to show it, so Johan did this nice plot where if we look at temperature and sea level pressure response again here, but it's showing how many number, so N is the number, how many members do we need to get a significant response if we look at year 2 to 6 of the simulation, or 2 to 11, and I'm focusing on the summertime here for air temperature and sea level pressure. So blue here is about less than, this is 10, 20. And if you see some green and yellow, it's over 70 or 90 members. So overall, for the North Atlantic, you don't need that many members. But if you need to capture teleconnection over the Pacific here, you need over 50 members to get them. And it depends, of course, what the length of the chunk you're going to look at. And if you look at 10-year averages, then there are other teleconnections that appear. And so to get all this Pacific response, for example, in terms of sea level pressure, you need over 30 members. You start having it from 30 members, but the significance increases. The area where it's significant increases as you increase the number of members. Another way to show it is what would we capture for the signal I showed with just some given number of ensembles, sorry. So for the temperature, again, just for the summer, if we have 25 members, we of course get the pattern we want to impose there, but the Pacific response is quite limited. And from 50 members, we start getting this PDO-like response. And then I would say that we refine the things, especially over land, but the pattern doesn't change that much. So I would say that 50 for this type of experiment is probably the magic number. Yeah, I'm done, actually. Same thing for sea level pressure here. You see some differences in the extratropics, in particular for the summer here, starting from 50 members, and then in the tropical Pacific and North Pacific as well, but it doesn't evolve that much. But one thing to keep in mind is this is true if we look at the mean response, but then even if you say the magic number is 50 here, if you want to look at extremes or number of cold days, or you will need more, right? So we still think that 100 is needed to look at the extreme events associated with the AMV. So, but it depends on the resources of each group, of course. So my conclusion is that this, to run this Atlantic pacemaker experiment, we believe that we need to restore both temperature and salinity to not perturb the system too much. These results might be model dependent because the adjustment are going to be very different from one model to another. But if we want to make sure that we propose a protocol that will work in all the models, I believe salinity is a requirement. So the time scale, which time scale should we choose? I think we need not a too short time scale. So 5 days too short. This is for 10 meters. So I think 15 days is the minimum we need. This is the number we need to put, or longer. So we need also tropical anomalies to get the full response of the AMV and the teleconnection that are associated. Going only north of 20 north, I think we miss a lot of teleconnection that are important. keeping in mind that by having a coupled framework, we can mask some of the direct response to the AMV. So there are teleconnection, and this is what we want actually to see also. What are the teleconnection from the other ocean? That it's very interesting with respect to fixed AMV pattern, but we need to keep in mind the interpretation. And then, yeah, how many member ensemble we choose depends on what we're going to look at, variables, extremes, or mean response. But I would say that 50 members might be the minimum to get significant global response. So thank you very much.
Thanks, Rim.
Thank you for the comprehensive investigation relevant to component C. And my question is on SSS restoring.
Yes.
You convinced us that the SSS is necessary, but for the climatology, you use SSS pattern of the model climatology.
Yeah.
But how about the anomaly? How is SSS pattern used in your results?
Yeah, this is exactly what we're facing right now. This is a good point. I didn't have time to touch it. So once we realize that, now we're repeating this AMV experiment, restoring the AMV. We don't want to impose salinity anomaly that are associated to the AMV, because what we want to test is really the impact of the temperature. But what we need is to define the salinity that compensates the temperature in terms of density. So what we are trying to do now is, from the equation of state, go back and find the salinity anomaly that, using the UNESCO equation of state, are going to compensate for the salinity. And you're laughing because it's not easy business to do. And Johan is struggling these days. So if you have advice, he's, I think, happy to take them. But this is, yeah, it's not an easy thing to do. But it's probably something we need to discuss also here as a group. What are the alternatives? There are any. But
Steve and then Ren.
So if I understood you correctly, you argued that the reason why you get an AMOC weakening is because your restoring is more effective in summertime when mixed layers are shallow. Couldn't you do some sort of seasonal cycle of your restoring time scale so that you can restore winter temperatures more effectively?
yeah, I think that, I don't know if there were tests of that. You did that, Christophe? Or yeah, this is what? By changing the restoring coefficient, right? Here we use a fixed restoring coefficient, and Eric is going to show that using latitude dependent, mixed layer depth dependent, sorry, which makes sense because the mixed layer, we cannot assume that the mixed layer of 50 meters is reasonable for everywhere between the tropics and high latitudes. And it's very physical to take a variable mixed layer. So we just took a fixed one initially because it's the simplest, but it might not be the best, yeah. So yeah, we should test that, it's true.
Just a comment on your last point. So you can make any size anomaly, any arbitrarily small anomaly significant by increasing the ensemble. So keep increasing, smaller and smaller anomalies get significant. Where it doesn't help and where we miss the point is, now if you use this as prediction, you have to make a 100-member ensemble forecast, and what's actually going to happen in the observation could be any one of those 100.
Yeah.
So that doesn't help you at all. So comparing 100 versus 10, so if you needed only 10, that will be much more helpful in making the prediction versus 100. So you can make anything significant by increasing the ensemble size.
Yeah.
But its predictive value keeps going down.
I agree with you, yeah. Yeah. But how to infer which anomalies will be predictable for a given ensemble size is not straightforward from this, yeah. So we cannot assume from this that because we're running this 100-member and we get this significant anomaly, then in the component A, it means that the models that are able to reproduce this AMV will be able to capture all those teleconnection. I agree.
Yeah, just to continue on that, both the SSS and restoring. So, as you mentioned, there are some results more about using restoring as a function, both time and space dependent on the mixture depth. Quite interesting results. Now the salinity, when you were in the model world, it's okay, you have salinity. Back on the historical framework, we're faced with what to use. We know SST. What about how can we find the SSS product that would work. So also I wanted to perfectly understand why you want to use the equation of states.
Because we don't want to impose the SSS, this is the thing. So here we're not wondering whether we have observed salinity to impose, because we don't want to impose density anomalies. We want to impose the AMV temperature anomaly here that the atmosphere will see. So we just want to put the salinity that will compensate for this temperature so that we don't get density anomalies. So in a sense, we don't need salinity observation, so that's a good news. But then we need to compute those salinity. And when for a pacemaker experiment, it's not a single computation. It means for every month, if we do monthly variation, we need to find those values.
Dirk, and
So, do you think we need a full ocean model for these experiments, or will a mixed bag?
Yeah, I'm not sure actually. Yeah, I think probably having a couple model in the Atlantic makes things more complicated. So probably having a mixed layered model in the Atlantic and coupled elsewhere would be better, but then you need to think of having a buffer zone between the Atlantic and the other regions. So it's not necessarily that easy if we don't have exactly that simulation, for example. So for us, developing it requires more resources, and other groups might be the case. But yeah, I think we need both to make sure that the anomalies that are created as a subset are not communicated to the other basin, but still keeping the free coupling elsewhere. I wish we could keep it as all coupled, but it's probably bringing more problems than gain from my point of view.
Since you are already commenting on the component C, why are we forcing the model to have something that it's not doing?
Because we want to test that, and we know the model is wrong, but we're not interested in the model AMV because we know it's wrong.
But it's the model AMV. I mean,
But users don't care about the model AMV if you're thinking from a user perspective.
I mean,
right?
we are thinking about how understanding decadal prediction. So we are going to use that model, or the new generation of GFDL model, to do decadal prediction, and that model is not going to produce this sort of AMV. So the whole philosophy, I'm not saying that it's wrong, but I'm just asking the question. We should ask ourselves again, why are we forcing the model to do something that it doesn't want to do?
Yeah.
And why do we trust the response if it doesn't do this right?
It's not because it's not able, as a free-running model, to have the right AMV, then that it means if you don't put the anomalies there, it has a wrong teleconnection. These are distinct issues.
I guess this is saying if the model was right, this would have happened.
Yeah.
And that's the thing you want to chase and make the model better.
And as DCPP, we can continue that work on the model world, making our model better and caring maybe less about the users there.
Paco and
I found your argument about the collision of the North Atlantic response in terms of zero pressure coming from the Pacific. From a prediction point of view, that doesn't make sense because you want to have the full response. So I don't really know how to interpret these results. How to understand it.
The fact that it's masked, I'm not sure I understand. I didn't hear the beginning, sorry.
Oh, sorry. What I mean is that from a prediction point of view, you want the full signal. So there is not such an idea as a pollution from a different place. Either you have it or you don't.
But it could mean that in the real world, there are times where even if the AMV is positive, it's going to create teleconnection in other basins, and that will give you an ANAO+. So as an interpretation, as a scientist, you can say, oh, this year we have been having continuous AMV, but from our understanding, we expected an NAO+, but we are sorry we didn't provide you this good prediction because actually this was this teleconnection that now we understand happened. Maybe I'm not sure it's useful, but my way of looking at it.
the last two questions, Christophe and then Al.
Just to follow on the comments, we had this discussion in component C, which pattern are we going to, which pattern are we going to restore the model. What the difficulty we had is if we stay in the model world, we have to find a common metric to define the AMV in each model, and it's really difficult to find this metric because it's very multiple. So that's why we decided to restore to the observed pattern, which is really common to
The value of the comparison with the NCAR result is that we're using the same pattern that Mingfang provided us. And I think the result would be easier to compare because of that.
And follow on Doug's comment of the mixed level. I mean, I tried to build our model, and I came to very difficult issue on the buffer zone because I mean, basically North Atlantic is mixed level, and the rest is open. You have to deal with the heat transport, and you can make crazy things in the mixed layer. I mean, in the buffer. And I think it's, I mean, if we view this in terms of coordination of our competency, it's going to be really hard to come up with a solution.
On those springs up, Alan.
So this is probably a very naive question, and I'm coming at it from a different way. I'm not part of the community that does AMV, but what is AMV? Sometimes I ask if people say it's the complete circulation in the ocean, but now you're just forcing it at the surface. And if you put the trend back in, isn't it just the forced response by aerosols and tropospheric and by greenhouse gases of the climate change? So is it really the linear, take out the linear trend, is really just the forced response, or is it something fundamental that's separate from that?
Grim, you want to answer that?
Well, I wasn't.
Don't want to repeat the question.
The question was, what is AMV?
Scott can say this is AMOX. I think we don't know the answer to that. I think here we're taking this pattern from Ming-Fong because we think it's the best representation of the internal variability part of the AMV, which doesn't mean there is a force component in addition to that. So we're testing that, but then it's another, like a variety of work trying to understand what creates this anomaly. And this is maybe part of the work that can be done on Calibre DCPP, but we're not really answering that question here.